We can start. Okay. Are you ready?
I think so, yes.
No.
But yeah, actually, I'm not in Caen anymore. Now in Brussels, just as a disclaimer,
Yes,
as a
I
general
see.
disclaimer,
I
because
see.
yeah, thanks for the thing is the
Okay.
logo fits very well into the color scheme of the rest of the talk. So
Okay. Okay. Fine. Dear colleagues, let us start our seminar. I am very glad to introduce our speaker, Professor Dietzel from Belgium now. He will speak about cabling and endocabling. Please.
shall I start?
Yes, yes, you can start.
Okay. Hello. Thanks for joining to my talk. Today I will talk about cabling and endocabling, and I will give a brief manual how to do cabling and endocabling. So, to give an overview over the structure of this talk, first I will introduce the main structures and that we are dealing with, which are essentially cycle sets, which are equivalent to certain solutions of the Yang-Baxter equation, and special algebraic invariants such as the permutation group and the permutation brace of a solution. Then I will continue to explain how to cable cycle sets or solutions to the Yang-Baxter equation in the classical way, which is a technique introduced by Lebed, Vendramin, and Ramìrez. And I will explain shortly how to prove things with classical cabling. I will then proceed to introduce endocabling, which is a generalization, and then show what you can actually do with endocabling. So the first part of our manual is introducing some basics. So what are the basic techniques, or what are the basics to know when you want to work with cycle sets? So first of all, if you're talking about cycle sets, you have to know what is a cycle set after all. So a cycle set is simply a set with a binary operation. I will always refer to this operation. Do you see my cursor actually?
Yes, yes.
Very good. So what is a cycle set is that left multiplications are bijective, and furthermore that these left multiplication satisfies the so-called cycloid equation, which appears in the theory of the Yang-Baxter equation, and this is no coincidence in the theory of Garside groups as a rule for left complements. So we assume that this cycloid equation is satisfied, and furthermore we assume that the so-called diagonal map, which is simply the diagonal of the multiplication table, is bijective. And this is actually a special condition, but we assume it all the time. And this condition is called non-degeneracy of a cycle set. And we will always assume that a cycle set is finite. And furthermore, the diagonal is bijective, so meaning that the solution or the cycle set is non-degenerate. So this is a nice and kind of fancy structure. So why do we actually need this? Well, it turns out, and this has been found by Rump, who actually introduced the notion of a cycle set. It has observed by Rump that cycle sets are in a one-to-one correspondence with a specific, or non-degenerate cycle sets are in a one-to-one correspondence with specific solutions to the Yang-Baxter equation. So, which are exactly the non-degenerate involutive solutions. So it turns out that there is a well-defined way of defining a solution to the Yang-Baxter equation by mapping the element x dot y and x to y dot x and y. And due to the bijectivity of the left multiplication maps, this is indeed a well-defined notion. And it turns out that this is a solution of the Yang-Baxter equation, which is a kind of a braided equation. Well, why are we having these, or why are we using these very specific conditions? Well, it turns out that cycle sets or the solutions parameterized by cycle sets allow an introduction or allow an application of algebraic machinery. And a very simple algebraic machinery is, algebraic machine is the permutation group of a cycle set. So what is the permutation group of a cycle set? Well, it is simply the group generated by the left multiplications in the cycle set. And I guess if you have encountered quantals once, you will have seen a very similar concept. And furthermore, we will later need the so-called lambda maps, which are simply the inverses of the left multiplication maps. And furthermore, we denote the action of any element in Gx simply by lambda G. And so, given the permutation group, you can already detect some very easy properties of solutions or cycle sets. One of them is indecomposability, where we call the cycle set indecomposable if any decomposition into two subcycle sets is trivial, meaning that if you decompose a cycle set into two components that are subcycle sets, then one of them has to be empty. And it turns out that indecomposability is equivalent to the permutation group being a transitive permutation group, which is not difficult to show, but you already see that that there are some properties of cycle sets that translate to algebraic properties, but we will encounter more later. So first of all, let's give some examples of two cycle sets and their permutation groups. One very primitive example of a cycle set is a cyclic cycle set. You simply take a cyclic group of order n, and you introduce the operation x dot y equals y plus 1. And it's easy to see that the permutation group of this object is simply the cyclic group of order n, which acts regularly on set n. And furthermore, by the previous result that I've shown you, we see that this is in fact an indecomposable cycle set. Another cycle set that is indecomposable is the set 1, 2, 3, 4 with the following multiplication table. And it can be checked that this cycle set that is indeed a cycle set, and furthermore that its permutation group is a dihedral group of order 8, or one could also say it's the 2-silo subgroup of S4, or 1-2-silo subgroup of S4. And what we see here is actually something very specific, namely that the rows of the multiplication table are different. And one might assume that typically a generic cycle set should have always different rows, or very often, but this is wrong. In fact, a generic cycle set seems to actually tend to have repeated rows. And this concept, or this phenomenon, is captured by the notion of retractability, or the notion of retraction of a cycle set. Because it turns out cycle sets tend to have repeated permutations. And if we now identify rows that have repeated rows that are equal in the multiplication table, then in fact we get a congruence relation. So given a cycle set, we can so define a congruence relation, the so-called retraction relation, by identifying x and y if and only if their left multiplication maps are equal. And it turns out that if we factor out this relation, we again get a cycle set. So it's a genuine congruence relation. This is called the retraction. So the result of factoring out the relation is called the retraction. And it turns out you cannot only do this once, you can often do this a few times. And so we are given so we can define the so-called retraction series. So we take, or this is actually not a genuine recursion, it's actually an iteration. So we define the zeroth retraction of a cycle set simply as the cycle set itself. And then we define the k plus 1th retraction as the retraction of the kth retraction. So it's simply, so the kth retraction is simply the result of applying the retraction k times. And this gives rise to the notion of multi-permutation level, because often this we can repeat this retraction process until we cannot retract for the reason that our cycle set only has one element. And this gives rise to the notion of multi-permutation level. Sorry for repeating. namely the multi-permutation level, is simply the first K such that we encounter a cycle set with one element. If we don't encounter such a cycle set because we get at some point stuck in a cycle set whose retractability relation is trivial, and that is of size greater 1, then we say the multi-permutation level is of size is infinity. So this means simply we get stuck at some cycle set that is also called irretractable. So you cannot retract it anymore. And it turns out that retractability is very intimately related to other notions, other algebraic notions, which are related to the so-called brace structure of a permutation group. Before we talk about this brace structure, let's talk about braces in general. These are also a tool that has been established by Rump in order to algebraically analyze cycle sets. And first of all, what is a brace at all? Well, a brace is simply a set with two group structures, plus and dot, or I also say plus and multiplication, such that the additive group structure is an abelian group structure. And furthermore, we have this kind of fake distributivity law. And given such a structure, we get, in fact, that the multiplicative group actually acts on the additive group by the so-called lambda action. And this is simply this action which is defined like this. Oops. And it turns out that with this so-called lambda action, the additive group becomes a module over the multiplicative group, which is an important fact that we will need later for talking about endocabling. So we have an action of the multiplicative group on the additive group, and given this action, we can introduce two very important invariants of a brace, which are the socle and the fix. And the socle is simply the subset of all G that fixes the whole of B. One can also say it's the kernel of the lambda action. And on the other hand, one can also talk about the invariant elements under the lambda action, which is the fix. So everything which is fixed under the lambda action is in the fix. And these are very important invariants, and that are very useful in order to prove some stuff. We will see later. But first of all, how are braces related to the Yang-Baxter equation? Well, it turns out that you can turn each brace on one hand into a cycle set. Namely, one can simply take the lambda action and invert it. So if one takes the lambda action of A on B and inverts it, then one gets a cycle set structure, which is also called the cycle set associated with a brace or the canonical solution associated with a brace. But on the other hand, there's also a way of getting braces from cycle sets, which is simply by taking the permutation group and defining an abelian group operation such that you on one hand get a brace, and on the other hand, the lambda action of the element lambda x on the element lambda y gives you simply the element lambda of lambda x of y. So in some sense, you demand that the map that maps x to lambda x is a homomorphism of solutions. So this means you get in some way some kind of transfer from cycle sets to braces and in the other direction. Of course, this transfer in the other direction is not necessarily injective. So you might lose information, and this. So essentially, you don't get an embedding of a cycle set into a brace, but you actually get an embedding of the retraction. So it factors through the retraction. And one can see that if a cycle set is irretractable, then the socle of the permutation brace is 0. This is very important in order to prove stuff. So now we have all the, how do you say this, the ingredients to talk about endocabling. To talk about cabling in the classical sense, which is technique introduced by Lebed, Ramìrez, and Vendramin to prove certain decomposability theorems. So what are typical decomposability theorems? These are theorems that typically say that give AC conditions to recognize when a cycle set is decomposable. And typically, or the interesting decomposability theorems are those which relate the structure of the diagonal map to decomposability. And there's a very, how do you say this? The prototype of these theorems is the theorem of Rump, which tells us that if the diagonal of a cycle set is trivial, then a cycle set is decomposable. On the other hand, if the diagonal of a cycle set is an n cycle, full cycle, then the cycle set is indecomposable. This is not very difficult to prove, but these cycle sets are interesting, so I mentioned this. On the other hand, there's a theorem of Camorra and Sastrikis, which tells us that if the order of the diagonal is co-prime to the order of x, then a cycle set is again decomposable. And the original proof is a bit complicated, involves group theory, but it turns out that with the so-called cabling machinery, this proof is like maybe a third of a page. So what is the cabling technique? So the cabling technique essentially is a technique that deforms cycle sets. Namely, if we are given a cycle set, then we replace the multiplication in our cycle set by the operation lambda inverse of k lambda x of y. So if we put, for example, k equal to 1, then we simply obtain our original cycle set structure. And it turns out that this definition or this deformation again leads us to a cycle set which is in general different from the original one. And now the problem is, of course, when we have a procedure to deform solutions, then we should, of course, be able to have some control over how it behaves. And it turns out that using cabling, we get indeed some control over a typically very difficult to control invariant of a cycle set, which is the diagonal of the cycle set. Namely, it turns out that if we take the k-cabling of a cycle set, then the diagonal is simply of the cabling is simply the kth power of the original diagonal. We will encounter this phenomenon again in the context of endocabling, where something more general happens, but we will see later. But yeah, so we see that that diagonals behave very controlled over cabling. So this means if we deform a cycle set, or if we take a k-cabling, then we know exactly what the diagonal will be. And furthermore, another nice property of our k-cabling or of k-cabling is that we have some control over decomposability. Namely, if we cable by an index that is co-prime to the size of x, then we know that x is indecomposable if and only if the cabling is indecomposable. So we essentially preserve the property of being decomposable or indecomposable. And the proof is ridiculously easy. Namely, the k-cabling, we can show that the permutation group of our cabling is simply k times the original permutation group, where we take the kth multiple or the kth multiple with respect to the additive structure. So we get a whole pi subgroup. So we simply preserve the whole pi subgroup, where pi is the set of primes in X. And we know that such a subgroup still has to act transitively if the original group has acted transitively. So we don't kill the whole pi size, we don't kill elements of a specific whole pi subgroup, so we preserve indecomposability. And wait, have I already? Yeah, I've repeated this. I've just noticed. But yeah, so one property is if we cable by nice indices, then we preserve cabling. On the other hand, we have control over the diagonal. And that gives rise to, this gives us a very easy proof of the Lebed Ramìrez, of the theorem of Camorra and Sastricus. Namely, we want to show that if a cycle set has a diagonal whose order is co-prime to the size of x, then x is decomposable. Well, let's just assume that this was not the case. Then we take the k cabling where k is equal to the order of the diagonal. As we said before, indecomposability is preserved, but on the other hand, the diagonal becomes trivialized. But what does this mean? This means that our cycle set is decomposable by Rum's theorem. So we have an obvious contradiction here. Of course, this is not, how do you say this? One could in some sense say this is not an honest proof by contradiction, but we see what happens here anyway. And this is, how do you say this? This is a very standard proof technique, namely, we cable in a way such that we get a reduction to the theorem of Rump. It's a very standard way of proving stuff. And we see this is a pretty, how do you say this? This is a pretty easy and short and memorizable proof. And it turns out that you can do a lot of these proofs. And you see them, for example, in the paper of Lebed, Ramìrez, and Vendramin. They prove plenty of theorems using this cabling technique. And furthermore, you can also use cabling to decompose cycle sets in the sense that their operation is decomposed. Namely, one can in some sense take the so-called Dionois class, which is the exponent of the additive group, and then cable essentially everything out which is co-prime to one of the prime factors, or one of the prime powers that divide d of x. And so you get some kind of cycle sets that satisfy what you could call a mixed cycle set condition. And you can continue to analyze cycle sets locally in some sense. So cabling gives us a way to actually decompose cycle set structures into local structure, which is extremely valuable to do proofs. So the question is now, how can we go further? So first of all, why does, I have to see how we're on time. Oh, we have a lot of time. So now the question is, what is behind cabling? What is behind k-cabling? And can we actually generalize this to even prove more nice stuff? And this question gives rise to the concept of endocabling. So we have already seen that the additive group of a cycle set is actually a module over the multiplicative group. And it turns out that the reason why this deformation procedure goes so neatly is that actually the multiplication by k is what I call the lambda endomorphism of the permutation brace, meaning that it is an endomorphism of the module structure of the module structure of the additive group over the multiplication over the multiplicative group. So what is the lambda endomorphism? It's simply, as said, it's an endomorphism of the additive group as a module over the multiplicative group. So we demand that it's additive, so it preserves multiplication, or is a homomorphism of the additive group, and furthermore, we demand that it intertwines the lambda action. And we denote the set of endomorphisms by this. So it's simply the endomorphisms of B with respect to lambda. And as we should expect from endomorphisms, homomorphisms are preserved by composition and by addition. So if we add up two endomorphisms, we end up with an endomorphism, a lambda endomorphism. And if we compose them, we again end up with a lambda endomorphism. And it turns out that using lambda endomorphisms, we get a way more general notion of cabling. Namely, we can take an endomorphism phi of the permutation brace of a cycle set and deform the multiplication in our cycle set by this. So instead of replacing lambda x here by k times lambda x, we replace it by phi of lambda x. And it turns out we get a new cycle set. So in fact, this is a more general way to deform cycle sets in order to gain new cycle sets. And furthermore, we have some control over the permutation brace, because it turns out that the permutation brace, or the permutation group, I would say permutation brace is more precise here, the permutation brace of the cable solution or the cable cycle set is simply the image of phi. So now we have a technique, but can we actually get new examples of cablings? So maybe you have a nice technique, but nothing new happens because we don't have any precise, how to say this, example where we can do something more general. But in fact, there are in fact some instances of new cablings that occur. So let's give some examples. Of course, as said, the classical cabling technique we simply get if we take the lambda endomorphism that is simply given by multiplication by k. And it's easy to see that the cabling by this endomorphism is simply the k cabling in the sense of Lebed, Ramìrez, and Vendramin. Furthermore, this example is a bit artificial, but it's still an example. We can take an indecomposable cycle set, whose permutation group is a p group, and we take an element in the fix whose order is a power of p. And one can always show that such an element exists, which is even non-trivial. And then we define simply an endomorphism that maps each lambda x to the inverse of f. And in this case, it turns out that the cabling is simply the solution where each element acts by lambda f. So this is also an example. It's a bit artificial, but yeah, it's still an example. And a very interesting and useful example of a cabling is the cabling by the center. How do you cable by the center? Well, you simply take a central element and you take as an endomorphism the map lambda of z. This is easily seen to be an endomorphism simply because lambda z, of course, intertwines each other, intertwines the lambda action simply because z is in the center. So lambda z intertwines all lambdas, and so we get a new cycle set simply by replacing the old cycle set multiplication by, so we replace left multiplication by x by the left multiplication by lambda z of x. So we have some examples of cablings. So what does a non-trivial cabling now look like? I won't go completely through the following calculation. You will find also the slides on my homepage. Oops. Sorry, I missed the slide. Yes, so the question is, what control do you have over endocablings? Because now we again have a technique, and the question is, can we control more than only the permutation brace? Well, it turns out we can again obtain control or get control over the diagonal to some extent. So how do you do this? Well, it turns out that different cablings, first of all, that come from lambda endomorphisms are mixed. And this is a condition that has already been found by Feingesicht in the context of classical cablings. It turns out that these that endocable solutions satisfy a kind of mixed condition or a kind of matching condition. So, furthermore, if we now define T phi, so the diagonal of the phi cable solution, we we can actually get a way of calculating, to some extent, the operation of the phi plus psi cable cycle set, which is simply given by that. And it turns out if you use the above theorem, you can also reverse this and get something like t psi of x times over phi times x times an x psi times y. So you can use this theorem to turn this also around. And if we now also set x equal to y here, then we get that the diagonal of the phi plus psi cabling is simply the composition of the diagonals of the psi and the phi cabling. And this is a very useful property, because if we, for example, take, say, for example, we take for phi and psi the identity, then we get, of course, t of 2 times the identity is the square of the original diagonal. And if you iterate this, you see, or you obtain the result of Lebed, Vendramin, and Ramìrez, that the K cabling, or that the diagonal of the K cabling is simply the kth power of the original diagonal. And this generalizes this result. So we get that there is a map from the additive group of lambda endomorphisms to the symmetric group that maps a lambda endomorphism to the diagonal of the phi cable solution. And furthermore, what is also a very useful property is that the image of this homomorphism is abelian. And this gives you some constraints what a cabling can be, or what the diagonal of a cabling can be. So give me 1 second. Yes. So now given this, we can consider one specific cabling that we have seen before, namely the cabling by the center. And this is a proof technique that will turn out to be extremely useful later. So what can we say about the cabling by a center or by elements that come from the subalgebra of the lambda endomorphisms and that is generated by the center? Well, it turns out, for example, that we can do something that I consider to, or that I like to call cabling out the center. Namely, if we take a central element that is non-trivial, we can take the lambda endomorphism that is given by the identity minus lambda set. And this is kind of what you also know up to some sign changes as the star operation by x. And one can show that the image of phi set never contains z. This is a very useful property for proofs. And the proof is pretty easy. It's simply rewriting this and rewriting this as z minus lambda g of z. It turns out that this is never zero because under an automorphism, of course, a non-trivial element cannot be mapped to a non-trivial element, cannot be mapped to a trivial element. So we see that this is never equal to z. Easy. And furthermore, we can get a very nice abstraction for what the center of a solution can look like if we are given the diagonal. Namely, one can show that if we conjugate the diagonal by lambda z, where z is an element of the center, then the result centralizes the original diagonal. And the idea is simply, we know that lambda z is itself a lambda endomorphism, and we can compute the diagonal of the phi cable solution, in this case the lambda z cable solution, simply as t conjugated by lambda z. And as we said before, all cablings that come from the same we know that all diagonals that come from a phi cabling commute with each other. So we know that t to the z commutes with t. And this later is the key for getting some retractability results. You will see. So first of all, what can a non-trivial cabling look like? I won't go through the whole computations now, just to see what can happen. If you do cabling, you can, for example, define a cycle set by on set p times set p, where p is a prime, by this by this rule. where we demand that our parameter function phi is some non-constant function from set p to set p, which is even. And now we can take a central element which satisfies this, which is given by this. So we simply take each element in a set block and map, and so you say this, rotate it by 1. So we apply cyclic permutation on all blocks. And if we now take the homomorphism, the lambda endomorphism it minus lambda set, then we can calculate the phi cabling, the phi cable operation as this operation. And it turns out this is not a coincidence, that this is actually the action of an element of the fix. So it turns out that this element actually maps everything, so it maps the whole of G to the X to the fix of Gx. There's a deeper reason behind this, but I won't go into this now. We'll also not go through the calculations because, but you can check this out on my homepage. So you'll find the slides there. So now we have seen a nice technique, but having a nice technique is rather worthless if you're not in the position to apply it. So the question is, what can you actually do with endocabling? Well, it turns out that with endocabling, you can get some results about the structure of cycle sets whose diagonal is a cyclic permutation. Namely, you can show if you are given a cycle set whose size is an odd prime power, and furthermore, whose diagonal is a full n cycle, then the cycle set is retractable. Of course, one should probably say, of course, it's not retractable if v is equal to 0. So we should probably assume that n is greater than 1 for trivial reasons. And the proof is using endocabling, again, ridiculously easy, or almost ridiculously. Namely, one can first show that each cycle set which this property, namely that its diagonal is a full n cycle, is what I like to call a cycle set of pi type. So one can show that the primes that divide the order of g of x are exactly the primes that divide the order of x. This can be proven in a more general setting, namely for what I like to call irreducible cycle sets. But yeah, here specialized to this, we get that g of x is a p-brace, and by standard results about p groups acting on p groups, we know that there are elements that are fixed, and furthermore, there are non-trivial elements in the center. So we can get elements in the fix that are of order p, and we can get a central element that is of order p. And now we rewrite our cycle set, or we write our cycle set now. We identify our cycle set with a cyclic group of order set p to the v, and we assume that our that our diagonal is simply a shift by 1. And one can show that lambda f, we have seen this before, has to commute with the diagonal simply because you can, for example, consider the cabling. Or you can consider lambda f as the diagonal of the cabling. This is one reason, or one explanation why this commutes with t of x. And so lambda f has to be actually in the cyclic group generated by t of x, simply because t of x, this group acts regularly on x and is abelian. So lambda f itself has to be an element of this group, and so we know that lambda f has to be of this form. On the other hand, we also know that t conjugated by x, t conjugated by z commutes with t. So we know that also t conjugated by x is in the cyclic group. T conjugated by z is in the cyclic group generated by t. So we know that lambda z itself has to normalize this group. So it's in the holomorph. And on the other hand, cyclic group, central elements act without fixed points. If we are given a transitive permutation group, so we know that we're looking for a fixed point free element in the normalizer of n. in the normalizer of T. And also, again, we get that lambda z has to be of this form. And so we see that, in fact, in our brace, the fix and the center intersect. And this means, in particular, they intersect in the focal, which implies that our cycle set is retractable. And this is the whole proof, this case. And it turns out the property that the diagonal is an n cycle is preserved under retraction. So the smaller solution, again, has a diagonal which is a full cycle. So we can repeat this argument and we obtain that each cycle set of odd prime power size, whose diagonal is a full cycle, actually is of finite multi-permutation level. So the retraction series or the retraction sequence always ends in a cycle set of size 1. And now the question is, well, what can we say if P is not odd? Well, then things get a bit more complicated. And in particular, the result as we have it now is actually false. Why? Because there's a very easy cycle, a very small cycle set, namely this one. You have seen this before, which has this multiplication table. And this, in fact, has a cyclic diagonal, but it's irretractable. And now the problem is why does this proof not work? Well, it turns out that there are fixed point free elements in the normalizer of the group generated by the diagonal that are not in the fix. Namely, it's simply this reflection. And so what has been a half-page proof, before now becomes a proof that takes over 6 pages in order to show that this is the only counterexample. So one can in fact show that this cycles are. Maybe I should say why I called this X419. Well, it's simply the cycle set X419 in the gap library of small cycle sets. Maybe there's a better way to name this. So, but it turns out it's the only counterexample because you can show if you are given a cycle set of even prime of a size 2 to the v, whose diagonal is a full cycle, then if the cycle set is not isomorphic to our counterexample, then our cycle set is in fact retractable. And again, we can see that either the multiple permutation level of such a cycle set is either finite, so our retraction series just avoids this cycle set and terminates in a cycle set with one element, or we will terminate at some point in this cycle set. And it's a complicated proof, so I will only give you a slight idea of what is actually happening, because it turns out, it turns out that if we take the cabling by this endomorphism phi minus lambda, it minus lambda set, then the diagonal is simply n by 2 cycle, or a cycle of size 2 to the v minus 1, which means that the exponent of our solution is quite big. And this gives us some, how do you say this? This gives us some weak point to attack. And one lemma that is important here, I should add something, there is something missing, is this what I call a replacement lemma. What does it say? So if we are given a decomposable cycle set such that the permutation group is a 2 group, and we are given an element of the center which has order 2, we can define a family of endomorphisms which are simply given by kth multiples of it minus lambda set for some integer that has to be chosen appropriately. And now if we assume that the exponent of this should not be gx, this should be gx phi here. If the exponent of gx phi is divisible by 4, and furthermore x phi is retractable, I should also add that something is missing here. The focal of this should be non-trivial. Then we will find an element of the of the phi cable solution then we find an element in the center of gx phi which has order 2 but is not equal to z. This looks quite technical, but the idea is essentially that we exchange how do you say this that we exchange a tentative central element which is of the form given here by another one of the same form which cannot exist, because then we obtain an element that looks like that. So in some sense, this exchange level, this replacement lemma, in some sense produces too many central elements for a cycle set to be irretractable. And the proof is quite messy, and I'm sure someone will find a neater proof here. So the proof strategy is we first show that the theorem is indeed true for cycle sets of order less than 16, and for the size 16 case, you need I use some constraint programming, which is already kind of annoying. So maybe there's something more elegant, and then we do the same as before. We identify X with a cyclic group of order 2 to the V. And we then show that if we have a counterexample, so we have an irretractable cycle set, then there has to be exactly one central element of order 2. Why not 2? Simply because if we are given 2 of these elements, we can compose them and we get a shift. And we know that a shift is already in the fix. So what we show then is that some cabling by 2 to the k of 8 minus lambda z is retractable for small enough k. This looks easy, but there's a few pages of arguments. While on the other hand, the Denoir class, so the exponent of the permutation group of this cabling, is divisible by 4. And then we use the replacement lemma to actually generate a second central element. And so we get a contradiction. And this is essentially, or this is a very superficial description of what is actually happening in the proof. But of course, especially step 3 is very involved. And I guess this can be, maybe there's an easier approach to that. So this is essentially what I had to say about endocabling and the results. And as many results as there are here, there are even more open questions that come up. Namely, we have seen that we have very good control over special cablings, but not all. And what would be desirable would be to say something about the diagonal in cases where we don't just cable by elements coming from the center of the permutation group. It would be way nicer if we could, for example, say something about cablings that come from the center of the group ring over the multiplicative group of the permutation group simply. So it would be nice to say something about what happens if we take a central element of our group ring of G of X and cable by this. So can we say something about diagonal and how it behaves besides that the diagonals, besides that this results in a homomorphism from the center to the symmetric group. So can we say more? Because we could say at least something when we cable by lambda z or by, say, elements coming from the group algebra over the center of G of X, but can we say more? Or cannot we say anything at all? Furthermore, we have said something about cycle sets whose diagonal is a full n cycle. And now the question is, how can we generalize these results? Because we are very reliant, or we are very dependent on the fact that we on one hand have non-trivial central elements to cable with. On the other hand, we are also dependent on the fact that P groups acting on P groups always have non-trivial fixed points. So this means the methods that we have introduced here don't generalize to cases where more than one prime is involved. So the question is, if we are given a general cycle set of size n whose diagonal is an n cycle, what can we say about retractability? Of course, if n is even, we can simply take something containing x for 19, so our potential counterexample, for example, as a factor, and multiply it or take the Cartesian product with such a cycle set of odd size, and we get something that is definitely how do you say this? That might be retractable, but for example, is not of finite multi-permutation level. So maybe it makes sense to actually answer this question first if n is odd. And the problem is I cannot even state this as a conjecture, because the first case that you have to understand has to be of size p squared times q, because there's a theorem of Sedon-Ogninsky that says if n is square free, then x is retractable either way. So in order to understand what happens in this case, one should try to understand what happens if n is of odd size and of the form, for example, p squared times q. And the smallest example to consider would be of size 45, and I don't have any computational evidence for this happening here. So I don't dare to state this as a conjecture. So it's really a completely open question. So does it generalize or doesn't it? So if you're interested in more, first of all, the slides are available on my homepage. Furthermore, these are my references. And just for completeness, I didn't draw the illustrations myself. Obviously, I'm very bad in drawing stuff. I had ChatGPT doing this. Thanks for your attention.
Okay, thank you for interesting talk. Please, any questions, remarks, suggestions, and so on. No. I have the following question. We know construction of ramp, maybe rump. I don't know what is correct.
It's rump.
Rump.
Yes.
Okay. He introduced the braces to study involutive set theoretic solutions for the Yang-Baxter equation. And
Yes.
if we have a brace, we can define new operation. In new notation, it was star A star B. It's equal to lambda sub A of B inverse. And under this operation, we have cycle set. Is it
Yes.
correct?
Yes.
And we use cycle set for construction involutive solution for the Yang-Baxter equations. And now, suppose that we take not brace, skew brace. Skew brace defined Guarnieri and Vendramin. More general construction, in this case, both groups may be non-abelian. And
Yes.
we can introduce the same operation, A star B and equal to lambda A and so on. Could you say something about this operation? Do you know something? What is this operation? Is it possible to use this algebraic system for studying non-involutive solution for the Yang-Baxter equation or not?
Yes, there's a paper of Rump. I think it's called a covering theory for non-involutive solutions of the Yang-Baxter equation. And he actually shows that there's no cycle set, no classical cycle set structure, but a kind of I like to call it this dissociated structure. So in fact, there's not one operation, but actually two. So and it turns out that there's what he calls a Q cycle set, which actually has two binary operations that are kind of intertwined. And it turns out that if these two structures coincide, then all equations of what Rump calls the Q cycle set become one and the same equation, which is the cycle set equation. So the cycle set equation essentially splits up into three different equations that relate to operations of a so-called Q cycle set.
And you can use these two cycle sets for studying non-involutive solutions. Is it true?
I'm not so much of an expert concerning non-involutive solutions.
Okay.
But there should be theorems that so at least you get some kind of Q cycle set structure for example, on a more general structure. For example, what is called the so-called structure group of a solution, or a structure brace, or structure skew brace. And then you have, for example, embeddings, which is, for example,
it's possible to construct some analog of a cycle set if we start with skew brace. Is it true? And
this should be true.
You told about the paper of Rump covering of, could you remember? What is this paper of Rump?
What do you mean?
You say that Rump write some paper where he studied non-involutive solutions using skew brace.
Yes.
What is this paper?
What do you mean?
You say the title of this paper, covering of...
yeah, covering theory of non-involutive solutions.
Covering... okay, thank you. Thank you for...
And it should be possible. I'm not, as said, I'm not an expert with non-involutive solutions because they are kind of less well-behaved as the involutive ones. But what you can say is that you can use cycle sets to start so-called Q cycle sets to study non-involutive solutions. And you can furthermore identify these Q cycle sets of subsets of other more generalized Q brace-ish invariants. And this is, for example, used by, I think it's by Van Antwerpen and Colazzo, when they define cablings in a non-involutive setting.
Okay. Thank you.
So it turns out that skew braces, again carry the structure of a solution of the Yang-Baxter equation, and these solutions can again be translated into Q cycle sets.
Okay.
But you will often not see the notion of a Q cycle set. So I guess many authors also avoid using cycles, or you find a lot of articles where actually the use of cycle sets or Q cycle sets is avoided, and equations are simply written down as they are.
Okay.
Which is a matter of taste.
Okay. Thank you. Any questions? No. Let us thank speaker again. Thank you. See you next week.